Welcome to 2.2 Polynomials of Higher Degree. Let's get started. By this point, we know that the graph of y equals x squared looks something like this, and y equals negative x squared. We certainly should know this one at this time, that negative x squared, the graph looks just like x squared except post function times 1. The heights are opposite, so it's upside down. Now what they're really getting at here in this lead coefficient test is what we'll be referring to as end model behavior. We'll talk more about that, but that's typically how this is discussed in your calculus classes, end model behavior. In other words, what does the graph eventually do? So this graph, y equals x squared, eventually is rising to the right. So what's it doing is, as we move on and on and on, how can we describe it as we move on to the right? Oh, it's rising. As we move to the left, it is also rising. Now it is falling from the left, but it is rising to the left. So we always handle it that way. End model behavior, this graph is rising to the right, rising to the left, falling to the right, and falling to the left. So that's x squared. Now y equals x cubed. We should probably have a pretty good idea what that looks like. If not, put in 0, get out 0, put in 1, get out 1, put in 2, jump all the way up to 8. It's actually completely flat here just for an instant. Put in negative 1, get out negative 1, put in negative 2, get out negative 8. Completely flat for an instant. And therefore y equals upside down x cubed looks like something like that. And that's what this first section is about. It says if we have a polynomial, and each of these are simple little polynomials, and the first term is some a sub n. That's just some number, x to the nth. When n is odd, we are either rising to the right, and this graph falls to the left. In other words, approaches infinity as x gets big, approaches negative infinity as x gets little, or the exact opposite. If this graph was upside down, it would be falling to the right, rising to the left. And it's all about whether the graph's positive or not, or whether the function's right side up or upside down. If it's right side up as x gets big, graph becomes positive. So it's all about, it's the even odd test in combination with the sign. So if I have let's say I have f of x is negative 4x to the fourth minus 3x squared plus 2x plus 5, and we're asked for end model behavior, this eventually becomes the dominant term. Eventually the graph is going to try to look like that guy. And that guy, we should have a pretty good feel, just by itself, looks something like this. So this graph falls to the right, falls as we move to the left as well. So that's what this first little section's about. Well, big section here in the problems. Now the second, a lot of what we're going to be doing the next couple chapters could just be called the search for zeros. Oftentimes we're very interested when functions pass the x-axis. So if we have a function and it's a polynomial, if x equals a is a zero of the function, in other words, if I put a value in here as a, some number, if I put some number in here and it turns this into 0, then it's a zero of the function. And then of course a would be a solution to the polynomial equation f of x equals 0. I mean, these are virtually synonymous right here. This is really the biggie. X minus a would be a factor of the polynomial, and you'll see what we're doing with that. And If I go to the right A, the graph's going to be up 0. So this is talking about the function, but that's pretty much the exact same thing as talking about the graph here. If x is a 0 of the function, then a0 is a x-intercept of the graph. We go over a, we go up 0. We put in a, we get out 0. And then here they talk about zeros that are multiplicity 2, multiplicity 3. For instance, if I had f of x equals x squared times x minus 2 times x plus 4 to the third. Our zeros would include 0, because if I put 0 here, I get 0 squared 0 times whatever that is. 0 times anything is 0. But that is a multiplicity 2 0. And it affects the way the graph looks. And it's really kind of an interesting study. We'll be talking about that. 2 is a0. And negative 4 is actually multiplicity 3. It's a 0 multiplicity 3. You could think of this as x plus 4 times x plus 4 times x plus 4. And it's very interesting how that affects the graph, and we will certainly be talking about that. But let's go ahead and get into some example problems here. So here we have a big matching section, and actually we know a whole lot more about this at this stage than what the author thinks we know. The author really thinks we pretty much just kind of know rises to the right, falls to the left. But this graph right here, 12, passes through 1, and as it passes through, so we're passing through 1, as it passes through 1, it's going down to the right, up to the left, because for a little bit it wants to model negative 3x. But eventually it's going to look like a positive cubic, and you're going to see a lot of this little hieroglyphics from me. So I'm looking for a graph that goes through 1 and goes down. This graph goes through 1 and goes down. And then eventually, and I'm just talking about to the right, goes through 1, goes down to the right, and eventually goes up to the right. So far, so good. To the left. It should be going up to the left and eventually going down. Up to the left and eventually going down. And it does go through 1. So far, this looks like A. This graph doesn't go through 0, 1. This graph doesn't go through 0, 1. Nope. Nope. This graph doesn't go through 0, 1. This one doesn't. This one doesn't. So there's a lot of ways we could have come up with that, but I really like that little hieroglyphic approach. So this graph, number 10, goes through 0, 0. So if I'm just looking for that, B looks like it's a candidate, C looks like it's a candidate, E looks like it's a candidate, G looks like it's H looks like it's a candidate. We're going to need to know some more stuff. As it's going through 0, 0, it wants to look like the line negative 4x temporarily, pretty steep downward. And eventually it wants to look like a positive parabola. But we read this from right to left. Goes through 0 going down. Let's see, this doesn't go through 0. Goes through 0 going up, it's out. Goes through 0 going down, so I'll just put a dot here. So far C's in the game. Goes through 0, that's actually a double 0. We'll talk more about that. But it's definitely not going down through 0. Goes through 0, but it's going up to the right. Goes through 0 going down, so this one gets a dot. And now let's take a look. Eventually it wants to look like a right side up parabola. Well, my two dots here, this one eventually goes down left, down right, and our end model behavior should be up left, up right. So we have H here. Okay. Goes through negative 4/3, then wants to look like a right side up parabola. See, there's a 0x here. It's actually going through negative 4/3 flat. And then it wants to look like an upside down parabola, but eventually it's negative odd, negative cubic. Eventually it does this. So it doesn't go through negative 4/3. Looks like it goes through 0. Looks like it goes through 0. This one might be it. That might be below 1. And that's the only one it could be. But let's look at all of this as we move to the right. Okay, apparently that's negative 4/3. And then it's looking like a parabola here, positive parabola, just for a minute, until eventually to the right it turns back down. And to the left, it just kind of gets fortified up. There's D. And let's see, 16, there's like a plus 0 here. It wants to go through 0. We had a few of those. It wants to go through 0, wants to go through 0 going up to the right because we have a positive slope line. And then it wants to look like a negative cubic before eventually it looks like a positive to the 5th. So let's see. Doesn't go through 0. Goes through 0. Let's just talk about to the right. It wants to go up and then start trending down before it goes up. It goes up, trends down, goes up. Well, let's take a look to the left. It goes down before it comes back up, before it trends up, and then trends down. Goes down, up, down. Boy, it sure looks like it's B. B's in the game. Let's see. We know it's not C already. Doesn't go through 0. Goes through 0, but is not going up through 0. Goes through 0. It's actually flat there. It's not going up through 0. Now it's flat and then up, so it can't be that one. And that goes through 0, but it's going down. So this is B. Okay, now we are to sketch the graph of f of x equals x cubed, and this will be pretty tight. I think I'm really tempted to kind of spread this. I think I'll just graph it the way it is. Every tick mark is an increment of 1. So put in 0, and we get negative 3. Negative 3 to the third, however, is negative 27. Doesn't even fit on the graph. So it might be more valuable to put in our MyVox. But let's put in plain old y equals x cubed first, because we're supposed to do that. Put in 0, get out 0. Put in 1, get out 1. Put in 2, get out 8. 1, 2, 3, 4, 5, 6, 7, 8. Off the graph. Put in negative 1, get out negative 1. Negative 2, get out negative 8. And as I said, this is completely flat momentarily. Completely flat momentarily. That actually becomes a pretty important concept in calculus. So that's x cubed. And now we could go ahead and put in 3 and put in 4 and put in 2 and put in 1, but we shouldn't have to. This is our whole pre-function here. The MyVox is 3. That implies x value of 3. This is a 3-day delay. What normally happens on day 0 now does not happen until day 3. At day 1, we're usually up 1. Well, that's a 3-day delay. So 4 gets us to 1. 2 is up 8, but if I delay that 3 days, that takes me over to 5 to get up there. Left 1, down 1, but we're shifting to the right 3. 1, 2, 3. And left 2, down 8, shifting to the right 3. 1, 2, 3. Momentarily flat. The graph looks the same, it's just all shifted to the right 3, and we've certainly practiced that. So this one, there's 17. I shouldn't have done 17. I'll leave 18 for you. Number 20, if we were just doing this the way we were calling out or writing down what our shifts are, this looks just like x cubed, except it is right 2 and down 3. So what was 0, 0 here goes right 2, down 1, 2, 3, right here. That's like our most interesting value on the graph. And then what was right 1, up 1 was right here. Take this point, translate it right 2, down 1, 2, 3. And what was at 2, 8, 2, 8, right 2, 1, 2, down 3, 1, 2, 3, is now at 5, 5. This is momentarily flat right here. Guess I can put one more in. What was left 1, down 1, right 2, down 1, 2, 3, momentarily flat right here, up through there, down, and our next one is well off the graph. And I'm not concerned if you don't repeat the parent graph on every case. So I'm going to leave number 18 for you. Of course, that's a down 3. So same thing here. So I'm really just working off of these points, and it might be worth listing these. Here's y equals x squared. Whoops, xy. Put in 0, get out 0. Put in 1, get out 1. Put in 2, get out 8. Put in -1, get out -1. That's x cubed, excuse me. Put in -2, get out -8. And now we're just going to shift them. Shift them how? Well, what's the MyVox here? -4. This is a 4-day head start. What usually happens on day 7 would now happen on day 3. That's 4 to the left, where the MyVox is -4. We're 4 left, and we are up 1. So I can take each of those points, 0, 0. 4 left, 1, 2, 3, 4, up 1. 1, 1. 4 left, 1, 2, 3, 4, up 1. 2, 8. 2 just off the chart, 8. 4 left, 1, 2, 3, 4, up 1. Momentarily flat here, and then we're off the curve, or off the graph. -1, -1. 4 left, 1, 2, 3, 4, up 1. Momentarily flat through there, and then down to there. And the next graph, -2, 8, -2, down here just off the graph. 1, 2, 3, 4 left, up 1. Just makes it onto the graph. Okay, and that is it for the first page of 2.2. Don't think that one's going to take you too long at all.